How is it now? A bit loud, isn't it? This one? Microphone or the other one? Yeah, it's better, right? It's good.
Yeah, sure.
Yeah, it's good. Is it good in the back? Yes? Some noise coming out of here. Okay, let's see. Okay. Everything is good online? Okay, let's get started. Welcome to... Wait a second. Okay, yeah, this is the right starting slide. Welcome to the second lecture in memory-centric computing. Were you guys all here when Konstantina introduced the class? Okay, that's good, yeah. Yeah, I couldn't make it because my ankle was broken over the summer and I got the permission to fly and stand from my doctor after the class started. All good? Okay. Okay, so today we're going to have, how many people are here students who are taking the class? Okay, because I know there are some TAs also. Are there people online as well? On Zoom? Okay, on YouTube there may be people and we don't know who they are. Okay, it's good to come to class, I think. That's how you can probably learn better. So today, before your presentations start, we will have some presentations, maybe just one, on some cutting-edge topics in computer architecture. And I decided to cover memory-centric computing, which is a talk I've been giving in many places recently. I think it's an exciting area. It's an exciting topic. So I'm going to give it over here also with some slide updates. Does that sound good? Sounds like a plan? Okay, so let's get started. So this is the full title of the talk, Memory-Centric Computing, Enabling Fundamentally Efficient and Intelligent Machines. And in this seminar, hopefully we'll cover a lot of memory-centric computing papers as well as memory papers, because it's the major bottleneck today, as we will see in my lecture today. So this is a summary. Where is that static coming from? Is it my fault? It's a bit annoying. I tend to notice these smallest of things. Okay, other people are noticing it also, right? Okay, there's some static over here. I wonder if it's because of this or the other one. If we can fix it with the other one. Let's try it because it will keep on annoying me and other people, I'm sure. I think ETH needs to upgrade its infrastructure. Because we've had problems with the other place also, with the other lecture room. How about now? Better? Then you can still hear? Okay, that's good. Okay, basically it's a summary of the talk. Essentially today, computing has a huge memory problem. You may have heard of computing's energy problem. Some people have written papers about it. I would argue that computing doesn't have a big energy problem. It has a bigger memory problem, and it reflects itself as the energy problem. You cannot hear? Okay, it's tracked. Okay, all good. So computing certainly has an energy problem. I'm joking, of course. There's huge energy spent, but that most of that energy is coming from memory, essentially. And memory is responsible for other things also. A lot of waste in performance, a lot of waste in robustness, a lot of monetary costs, hardware real estate. Okay, this is becoming worse now. Robustness problems, example. What is this? Is there someone else who is connected to it, or? Huh?
I'm sorry.
Okay, it was you. Okay, yeah, as long as it's you, that's fine. Not the infrastructure. Okay, that's good. Yeah, and hardware real estate. A lot of the hardware real estate is there to design memory as well as interconnects. And this problem is becoming worse with more data-intensive workloads, like machine learning, for example. There's a craze going on if you haven't realized that yet. It's a bit of an unreasonable craze in AI and machine learning today, in my opinion. People need to become more reasonable, in my opinion, but there's that craze. Anyway, I believe we're doing fundamentally the wrong thing in the design of computing systems today. How many people have taken the digital design and computer architecture course with me? Okay, that's good, a lot. Any other courses with me? Anybody has taken? Okay, you're taking it right now. Okay, that's good, yeah. Oh, last year, okay, last year. Okay, that's good. So we've covered, for example, in digital design and computer architecture, a processor-centric way of designing things. Basically, we're designing things to be very processor-centric. And I think we can solve a lot of our problems by rethinking the paradigm of computation to be much more memory-centric. In this talk, I'm going to cover two major issues that we're having. One is at the level of technology scaling. Basically, we're having a lot of problems with technology, memory technology specifically. And I think we can solve a lot of those issues by having a more memory-centric approach and enabling memory to autonomously managing itself. Okay, I'm going to stay away from there. And I'm also going to look at the higher levels of the computing. Oh, no. This is so brittle. Seems like a lot of things are brittle here. Okay. Anyway, while you're fixing that, essentially, we're having a lot of problems with application and system scaling, meaning applications and systems are not scaling very well. For example, we're designing these larger and larger applications like machine learning models. And unfortunately, they're coming at a huge energy and performance cost. And that is actually causing us problems. I don't know if people online can hear. No? Okay, online's okay, except it's just this projection. Okay, I see. I mean, if it's just a projector, can I just log in on Zoom or this is?
That could be done from your laptop and share the slides. But
yeah, that's a possibility.
But people hear.
Oh, okay. Okay, I see.
So it's unstable.
Yeah, you can see we have a lot of brittleness. How do we get rid of the screen mirroring? Okay. So we have not designed how to, we have not figured out how to build robust computing systems yet, as you can see, right? These problems are never solved. There's always some issue with these connections. Okay, anyway. Basically, we can solve some of the problems that we have with a more memory-centric approach, but we should still be more cognizant about robustness issues. Okay, so that's kind of the summary of this. Now I'm going to go into a little bit more detail. Essentially, today we have a lot of workloads that are bottlenecked by data, in the sense that computing is really bottlenecked by data today. Important workloads are all data intensive, and they require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. I'm going to cover this because I'm looking at that really. And data is increasing. Essentially, we can generate more data than we can process, and we want to do more sophisticated things on the data. And clearly, machine learning is a really important domain today. And you can see in this picture that I borrow from Cerebrus' CTO, Sean Lee, the compute requirements are increasing exponentially and memory model requirements are also increasing exponentially. So that's why people are trying different ideas, like designing wafer scale processors that are this big so that you can put a lot of compute and a lot of memory together. Now, the problem is if you actually design a wafer scale processor, and if you don't design the memory right, you may not have a lot of memory on that chip. And these folks can easily put a lot of SRAM on the chip, but SRAM, as you know from DDCA probably, is not a dense memory technology. It requires 6 transistors, right, in the best case. And that's very expensive. And as a result, the number of, the amount of memory that they put in this wafer scale chip is 40 plus gigabytes, which is very small, right? Maybe they went to 80 at some point, but again, 80, 40, it's very small memory. We should really have memory on the order of terabytes and terabytes for large-scale applications. Okay, that's good to think about it. So basically, we have a huge demand for performance and efficiency in machine learning, but also in many other workloads like genomics, which we may touch into in this course, depending on which papers you select. but this is an area that we do a lot of work on, accelerating genome analysis and more generally biological sequence analysis. And essentially, we have very good data generators over here, things that look like this, the nanopore sequencing devices. And they can actually generate data at very high throughput, low latency. But analyzing the data that comes out of this using a genomics pipeline is expensive today because it takes a long time, especially if you want to make life-critical decisions, for example, in medicine, for example. So basically, we have a problem in how to analyze data in many domains. That's true for machine learning also. Okay, I can keep giving examples of applications like video, for example. We can actually generate a lot of data in video today. There are a lot of cameras everywhere. And this data needs to be ingested and analyzed depending on your goal, hopefully a good goal, hopefully not a bad goal. But technology, as you know from my DDCA lectures, is agnostic to morality and ethics, right? As much as possible, we should do good things with technology, but you cannot prevent bad things to be done by technology also, unfortunately. And there are many people in the world who want to do bad things with technology today. And anyway, essentially, the problem is we have a huge performance energy bottleneck. And the way we design our systems causes this bottleneck, essentially. We are causing a lot of energy waste by moving data between where the data is generated in the sensors, and then into the storage, and then into memory, and then into the processor finally, where it can be processed, and then back and forth while the processing is happening. This causes great energy waste because you're moving data a lot. But this also causes a lot of performance loss because you're essentially traversing a lot of interconnects to get the data to where it can be processed and then write the data back and then do this back and forth and back and forth. I put this in parentheses because performance loss is something that people have recognized many years ago, many decades ago, related to memory. As a result, people have developed a lot of techniques that we covered in DDCA, for example, caching, many levels of caching, many levels of prefetching, many levels of out-of-order execution, both in hardware and software, and also multi-threading. So all of these complicate the hardware and the software. In many cases, these techniques do not work perfectly. In some cases, they do not work at all. So caches are not very efficient, for example, unless you have very good locality in your systems. Prefetching may not work if you don't have good access patterns. Out-of-order execution may not work if you don't have very good parallelism, irregular parallelism in your program, right? Yes?
For me, loss would be defined in comparison to something we have less of.
Yeah.
Comparison to what are we?
Yeah. Comparison to basically a better paradigm that I will introduce. Yes. That may not exist at this point, right? Basically, we're losing performance. But if you had a different way of designing the system, we wouldn't be losing that performance. Make sense? Yeah. Basically, people actually try to alleviate that performance overhead. Or another way of thinking about it is performance overhead of accessing memory, right? Another way of thinking about it is what is the ideal, right? If you didn't have any overhead of accessing memory, what kind of performance would you get? And many studies show that if you eliminate that overhead, you will actually increase performance by orders of magnitude, let's say. That's another way of thinking. That's another baseline, if you will. But essentially, people design these techniques that make our systems much more complex. And when these techniques work, they somewhat improve performance. When these techniques don't work, they actually compound the energy waste because they're actually wasting energy. You're actually wasting energy going through the memory hierarchy, right? Even though it's not very useful for you. And also, they actually make our systems more complex, and more complexity in hardware is not good for sustainability because there is more carbon footprint that is necessary to actually design bigger chips. And if we are actually not getting performance out of all of those techniques that we're putting into hardware, maybe we shouldn't be putting them into hardware, right? Okay, so basically, the fundamental problem is today's computing systems are very processor-centric. All data needs to go through the processor to be processed because the other parts of the system doesn't have computational capabilities. And this comes at great system cost. And this is my picture that you may have seen in DDCA, for example, but this is a picture that I drew like in 2008. And if you look at this picture, there are a bunch of cores, which are the red parts. Today, they could be heterogeneous cores. They could be accelerators. And those are the places where computation can be done. The rest of the system, at least in this node, is dedicated to storing and moving data. There are caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, and then main memory off the chip, and then other interconnects, and then storage. So most of the system is really dedicated to storing and moving data. And if you do the calculations in a modern system today, more than 95% of the hardware real estate of a single node is there. And that real estate is dedicated to data storage and movement units, not computation units. So that's interesting to think about, right? I think I'd like to take a more fundamental perspective in these lectures, and in this particular lecture also. Well, what would we do if we were designing this system with a blank slate? And a blank slate, a child is a blank slate. When we were born, we weren't born with this knowledge probably, right? But we can learn, right? So take a 10-year-old child who is not unfortunately spoiled by education, etc. yet. If you don't like that, go to 6 years old. But you may have trouble with the 6-year-old communicating sometimes. But let's take the 10-year-old and ask the question. Tell them, I actually designed this system. More than 95% of the hardware is dedicated to storing and moving data. I should not have a problem with storing and moving data, right? And any reasonable person probably would say, no, you should not, because you're dedicating almost all of your resources for that thing, right? But unfortunately, today, we're still bottlenecked by memory. So I think we need to take a more fundamental or blank slate approach, like a 10-year-old. All of us should become like 10-year-old kids. When I give this lecture to like 50, 60-year-old industry veterans, I say the same thing. So be like 10-year-old kids. I think 10-year-old kid has a lot of advantages, right? They're not yet, let's say, indoctrinated by how we build things. They're not yet indoctrinated by how we educate people, as much at least. And they're not yet, they don't have any like business concerns. They're not making money out of this thing. They don't have any conflict of interest. So it's a good example to think about. It's also a good example to ask research questions with, right? What would a 10-year-old kid who is smart do if they were not really, let's say, indoctrinated in some way? Okay. This is another example. I'm going to give you more data. That was hardware cost. Hardware cost is expensive, basically, to deal with memory. Let's take a look at performance. We complicate our systems. Google did this study in 2015, which is a beautiful paper, which I think we used to put up as part of the paper list, but I don't know if it's on this list this year, because we keep changing the list also, because at some point, if people keep presenting the same papers, it becomes boring for me to see the same paper over and over. Even though every time you can think about something different about a paper, every time it's presented, because no two presentations of the same paper are the same, right? It may be presented by a different person. You may be a different person. You probably are a different person when that thing is presented. So if you guys have taken DDCA today, you would be a different person, because you have had 1 year, right? 1 year, less than 1 year, maybe, depending on when you took DDCA. Okay, basically, Google did this study in 2015. And they analyzed all of their data center workloads, and they found out that on the workloads that they execute in their data centers, most of the time the processor is waiting for data. That's what most of that backend bound is about. The processor is doing what it's supposed to be doing, which is completing instructions, retiring instructions. You're familiar with that terminology from DDCA, only 10 to 20% of the time. Again, let's take the example of a 10-year-old kid. Throw this picture at him, explain it a little bit, say, I'm designing the system. The goal of the system, the sole goal of the system, is to finish instructions. And the system is finishing instructions 10% of the time. This is a good system. Yeah, the 10-year-old kid would tell you, this is crap, do something else, right? The 10-year-old kid is very honest. I think people should be more honest when we design things going into the future. Of course, the problem is, right, there's money involved, and honesty becomes more difficult when money is involved. That's another fundamental thing, trade-off, right? Okay, so if you look at, that was performance. If you look at energy, energy is completely worse, essentially. We're looking at here the energy costs of different operations. Again, these are old numbers from Bill Daly in 2015, who was NVIDIA's chief scientist now. Essentially, the numbers have changed, but the differences have remained in terms of orders of magnitude. So a 64-bit double precision floating point operation is 20 picojoules. This is a very complicated operation. A memory access, a DRAM access, read or write, is 16 nanojoules. That's 800x difference over here. So, okay, today you can actually make things better, more efficient interconnects, more efficient memory, you can reduce that disparity to maybe 150x, 160x, but not much more below that. Meaning, if you want to amortize the cost of moving data to the processor, you have a huge cost to amortize in terms of energy, right? Again, this is not a dogmatic thing. This is an optimization problem. It could be a nice DDCA exam question, actually, going into the future, by setting up the problem nicely. We can ask the question, when does it make sense to move the data elements to the processor to amortize the cost of energy that's consumed by data moment? I think it's good to think about that whenever we move data going into the future from storage. And we're not even considering storage over here yet. So in order, if you make those calculations under some assumptions, some workload assumptions, etc., you'll find out that you will need to reuse the data elements that you bring in at least hundreds of times. Some people have done these calculations, actually. Wenmei Hu from University of Illinois, who's actually right now at NVIDIA, has done those calculations, and his numbers are on the order of 2,000 or so. In many workloads, you don't get that levels of reuse. In many workloads, you actually cache some data element, it comes into the cache, you never reuse it, and that gets invalidated in the cache. Most of the caches house dead on arrival cache lines, which is interesting, right? And we're still building these caches bigger and bigger and bigger. It's good to think about it. So energy is actually much worse. And if you actually make the operation simpler, this is a 32-bit integer edition, not a 64-bit double precision floating point edition. The disparity compared to a DRAM access increases to, at least with these numbers, to 6400x. So the numbers go crazy, right? And we're not even talking about storage, right? Okay. So again, if you take the perspective of a 10-year-old kid, maybe they would tell you, consider something else, maybe, right? As opposed to paying this penalty 6400x many times, consider maybe doing the computation, not moving the data, right? So what we're talking about is not rocket science in that sense. If you throw the things at the right people, they would come up with a good solution. But of course, it's not that easy, as we will discuss also later on. Okay, we tried to do a lot of studies, and we still keep doing studies, and I would encourage more people to do these studies where we try to understand the system level overall and to end-to-end implications of the data movement or the memory problem that we have. And we did some studies with Google, and this is with workloads like TensorFlow inference, Chrome browser, video encoding and decoding. And on average use cases, we found out that more than 60% of the total system energy is spent on data movement in these mobile systems. That's a big number. And these are average use cases. In worst case, the numbers actually grow. And again, these are memory resident workloads. We're not even talking about going to storage or sensors. Okay. More recently, we repeated the study with accelerators that Google designed. These are edge TPU devices, tensor processing unit devices, which you have seen in DDCA, if you've taken DDCA, systolic array-based accelerators. And we found out that on proprietary Google models that are used in the field, in the edge, more than 90% of the total system energy is spent on memory in the large machine learning models. I will get back to this, hopefully, hopefully we will have time. But this is an example. Like at the time we did these studies, LSTMs and transducers were the largest edge models that we had. Today, there are LLMs that are actually much more intensive potentially, depending on what you do. But you can see that most of the energy is really spent on off-chip interconnect and DRAM on these accelerators. And as you accelerate computation, whenever you design an accelerator, usually the acceleration of computation makes memory as a bigger bottleneck, right? Because you accelerated computation. Computation is much cheaper in terms of time. The Amdahl's law says that there is whatever remains, whatever it is that you didn't accelerate becomes a bigger bottleneck because it's occupying a bigger fraction of the time, right? And you all know Amdahl's law, hopefully. Okay, so basically we have a fundamental problem. And the problem is that processing of data is performed far away from the data. We're moving it a lot. We're moving data a lot. So how do we solve this problem? Clearly, you can make incremental changes, try to reduce the data movement, etc., in your algorithms. I think those are all good. They should be done. But the fundamental inefficiency really comes from our inability to do something else on the memory side. Basically, we cannot do computation with minimal data movement. We always have to incur some data movement, and we always have to somehow hide it with some techniques or minimize it. So our goal is really to enable computation where it makes sense to do so, where data resides, such that we have choices in the system, right? We should not be limited to doing computation far away from the data. We should also have opportunities to do computation near the data, near where the data is generated, inside the sensor, near where the data is stored in SSDs, near the DRAM or inside the DRAM, near the SRAM on chip, near the register file. Even those are actually cannot do computation today. So the idea of this is more data-centric architectures. I call this more memory-centric architectures. So if you look at the picture that I like showing sometimes, you've seen this at DDC. And today is an SRAM-dominated chiplet type of system. And a very small fraction of this chiplet can do computation. Most of it is really SRAM in the end and memory interfaces. But there are a lot of other places, DRAM, storage, sensors. And we would like to enable computation capability everywhere, essentially. And we can do this with a model that treats memory as an accelerator. We don't need to change everything completely. Because one way of thinking about this is changing everything completely. There is no central processing unit. Everything is equal. There are a lot of processors everywhere, but there's nothing that's called central, right? Everything is distributed. And you have distributed computation agents that communicate with each other, and you write your algorithms in a very distributed manner so that they communicate with each other and they complete tasks, essentially. I like that, actually. That's very good. That's more forward-looking than what we're going to propose. A bit harder to adopt because people in general don't think that way, right? People are very, again, single-threaded, if you will. They have the central CPU, and that central CPU does things. So if you have the central CPU model and less prone to distributed algorithms, then you have accelerators. And we're already designing a lot of accelerators because people figured out that it's important to design accelerators for different applications like graphics, machine learning, imaging, video, etc. Why not actually accelerators on the memory side as well? That's the idea over here. We put accelerators on the memory, storage, sensors. And this way, programming is hopefully easier. You don't need to think about a complex distributed computation, a different model, even more different model. At least it's an accelerator model that we're kind of used to. Okay, it's good to think about this, I think, because there's a bigger thing to be exploited going into the future, which is harder to exploit right now. Okay, so this is a full slide that discusses a lot of opportunities here and a lot of challenges as well. In the rest of the talk, I'm going to talk a lot about main memory, but I'm also going to talk a little bit about storage. And I think even though we want to do computation everywhere, I think main memory is very special because we can store a lot of applications in main memory today. And we would like to enable processing capability there. Then the question becomes, what kind of processing capability, what kind of computation do you put over there? Do you put a full processor or do you put some accelerator? What do you put over there? That's compute capability. And we're going to look at different compute capabilities. How do you design the capability and the controllers? How do you design the processors and communication units to enable this? And once you actually have computation capability over here, how should the processor change, right? The CPU, so-called CPU, how should that change going into the future? How do you design the software hardware interfaces to enable this sort of acceleration inside memory? How do you design the system software compilers and languages to make it easier for the masses to take advantage of, right? This, now we're going across the higher in the stack. How do you rethink your algorithms to take advantage of the computation capability, which may be quite specific to the type of computation that you have put inside the memory devices, because you may actually exploit some fundamental characteristics of the devices, as we will see. And my favorite over here is the theoretical foundations part, because nobody works on it. Everything else people work on. The theoretical foundations, as far as I know, nobody works on it. I'm happy to be corrected. And I'm happy to see colleagues in theory taking actually a real problem and solving it like this. And I think this is a real problem. So what is the problem? Essentially, how do we develop a theory that's much more data-centric or memory-centric, right? How many people here have taken algorithmic complexity theory course, or where you quantify the complexity of algorithms? Okay, probably a lot of CS folks. Which course was it? The name of the course, if you remember. Yes?
Theoretical computer science.
Okay, yeah, so you did big O notation, big theta notation. Yeah, okay, that's what I'm talking about. Yeah, that sounds like a good name. Theoretical or complexity theory, sometimes people call it that way, right? Or computation theory, a bit different place. Theory of computing. I think when I took the course at Michigan, it was theory of computation. And we used this nice book by Michael Sipser, It's a nice book, actually, if people are interested in it. But anyway, if you look at how we quantify the complexity of algorithms today, we use big O notation. It's essentially an order of magnitude representation of how much computation you do, right? But maybe it doesn't matter, right? Maybe everything I said so far says maybe that's not really important in the design of an algorithm. Maybe you should really be focusing on data movement, right? How much data you're moving. Or maybe you should have a combination type of metric to look at both data movement and computation, right, with their respective weights. So I think this theory needs to be developed, and I don't think we have it yet. So this also shows that how ingrained in our thinking in computing processor-centric paradigm is. We don't even have a theory that's data-centric. Yes?
But as far as I'm aware, we already have for example, the notion of counting memory accesses.
Yeah.
In big O notation.
Yeah.
Is that true?
Not really. I mean, yes, you do count memory accesses as load operations, for example, right? Potentially, right? It's not, big O notation usually doesn't really count the memory access as distinguished, but you could augment it. But you really need to have a notion of data movement also, right? Yeah. Normally, what big O notation does is how many operations do you need to do, right? Sorting, for example. How many operations do you need to do to have the sorting algorithm to work, right? Yes?
This is much more dependent on the exact architecture, right? Because now when you look at the algorithm, you just look at what does it actually do and not how is the memory moved.
Exactly. Yeah. Yeah, exactly. That's exactly what we need to develop going into the future, basically. How much dependent will it be on the architecture? Can we make it less architecture dependent, potentially? Can we somehow put data at the center, right? Because any algorithm manipulates some data, right? But today, we may not be looking at how that data is being manipulated. Maybe it's a set of different theories based on different types of architectural approaches. So there's a lot of potential here, basically. But again, I haven't looked at it enough. So, and I don't think we're going to develop that theory within this hour. But it's good. People are thinking. Yeah. Okay. So basically, we don't even have a theory for this yet. Okay, I should also say that this is not a new idea. There are a lot of smart people who walk this earth, and I think it's important to give credit to smart people. This is unfortunately, I see in the scholarship of science today, people don't reference fundamental works as if nothing happened, as if they're the persons who have figured this out all on their own. But that's not the case in general. If you actually do your literature search, not through ChatGPT LLMs because they're terrible at this. They're terrible at finding facts. At least that's been my experience. Maybe I'm not smart enough to communicate with these tools. But essentially, people have developed a lot of ideas in the 1960s, and these are two fundamental papers that they call this approach logic in memory. I'm going to later call this processing near memory because this is a specific type of processing in memory that they propose. They put logic close to memory structures, essentially. This is the second paper from Harold Stone, who has a beautiful textbook on architecture also. Okay, so the question, of course, is these people have thought about it. What's new today? Right. Why should we re-examine this idea? And over many years, people have looked at this idea, and unfortunately, it never panned out. So I think what's new today is we have nowhere to escape. I don't want to be the doomsayer over here, but I think we're kind of doomed if we keep doing business as usual, because people are going insane building these data centers and powering them with nuclear power plants and wasting the planet's limited resources on these things. And if we don't stop things, it's going to be bad. Anyway, that's kind of, it's not a joke, actually. It's real. It's happening, right? But basically, we have nowhere to escape because the applications are demanding a lot from us. We have a huge data access problem, energy and power bottlenecks, data movement energy dominates computation energy. I've been showing you all of these. But also, I think we're at a point where we cannot afford to waste more energy because it's basically a waste, essentially. There used to be a time in computing where you want to improve performance. Okay, you can waste a little bit of energy, 3%. I think today we should not be doing it, meaning we should be improving energy and improving performance at the same time. And also, there's a sustainability, which is really critically important. And we need to actually improve sustainability going into the future, which means we should not waste hardware either, right? So today's approach of trying to scale the applications and systems by throwing more GPUs at it wastes all of those metrics, including sustainability, right? So basically, in my opinion, if we change the paradigm, if we design much better hardware much better computation paradigm, by minimizing data movement, we can improve all metrics. And I'm going to give you some examples. I'm not going to quantify sustainability, but I think intuitively, this will also improve sustainability because hopefully we won't waste a lot of hardware to overcome the memory bottleneck. So that's the higher level applications and systems pushing us. But I'm going to start with memory technology first because I think there's a lot of things happening in the memory technology today. And since if you've taken DDCA, you have seen me talk about RowHammer, for example. But essentially, memory technology scaling problems are very severe today. It's not going well. We're having issues like RowHammer, bit flips in memory, which should not be happening, silent data corruption, essentially. And these could lead to safety, security problems. And these scaling issues can be solved by putting better memory controllers or better computation near memory, essentially. It's a very different way of thinking about memory-centric computing. But I think people should think about it this way also. If we are actually much more memory-centric in how we deal with memory, we can do much better because we need to do computation to solve these problems, and I will convince you of that, hopefully. And once you do that sort of computation near memory to manage memory, why don't you do other computations also? Right? Then the memory becomes a place where you do computation. Today, memory is designed, especially DRAM, is designed with a perfect perspective, right? DRAM actually has been the perfect memory for many decades. You don't get errors. People didn't have error correction codes in DRAM in general purpose devices. In servers, they added very simple error correction codes, but general purpose devices, there was no error correction code. So if you think about it, memory doesn't do any computation at all. But the mindset should change because memory cannot even maintain data if you don't do computation near it. And if you actually put computation over there, you change the mindset and do more over there. That's the idea over here. That's why I think of this as being very memory-centric also. And also at the same time, there are some emerging memory technologies that people are examining. These can enable new functions in memory, like analog operational characteristics, exploiting analog operational characteristics. I'm not going to talk about the emerging memory technologies as much, but I'm going to give you examples from DRAM, but this is an area that's also important. So basically, kind of we're squeezed in the middle. Devices and circuits not scaling, they're asking us to do something different. And industry is doing something different finally, as you will see. And also applications and systems are not scaling very well, and they're asking us to do something different. And also, I think this is also happening, but it's a bit harder than technology scaling, because if you get bit flips, you have to prevent them. Otherwise, the whole computing stack will not work, right? Okay. So let's jump into memory technology scaling. That's going to be the first part of the talk. So we actually built a lot of infrastructure in my group to understand these scaling issues. This is one example. There are FPGA-based infrastructures where we can attach memory to programmable memory controllers. And these programmable memory controllers, we can program and test different timings to memory, test different temperatures, test different voltages, and access memory using different patterns so that we can understand what's happening in real memory devices. So this is fascinating. We built this infrastructure originally in 2011, and this has been improved over time. This is our laboratory a few months ago, some number of months ago, at the F floor of ETZ building, where we can test a lot of memory devices. With the new FPGAs we have, we should have almost 100 FPGAs to test these. And if people are interested in doing this sort of understanding and discovery of memory, we'd be happy to work with you. And I think we're going to cover some papers if you select them on this topic. So these are some of the infrastructures. We can test a lot of different DRAM chips. This is the infrastructure where we did a lot of RowHammer experiments on. This is at CMU. And this was the makeshift infrastructure that we developed originally in 2011. So it's grown a little bit. And we open source these infrastructures, SoftMC, and more recently DRAM Vendor. And a lot of people, both in industry and academia, have been doing studies with it. So one of the things that we have studied very heavily with this sort of infrastructure is RowHammer. And if you don't, how many people know about RowHammer here? Okay, how many people do not know? Okay, that's good. That means I get to explain it again. Yeah, but basically RowHammer is the fact that you can induce bit flips in real memory chips, DRAM chips. So DRAM is the main memory that's used in almost all computing systems today. All of these have DRAM basically. And if you design a computing system that doesn't have DRAM, you probably don't get much out of it. It's good to think about it that way also. But basically, all of our main memory is like this, and you can induce flips by doing a particular access pattern. So if you look at DRAM, it has two-dimensional arrays of cells that look like this. It's called a subarray. Now, if you activate one row, you apply high voltage to the word line that is connected to that row. And you do this to read one cell or multiple cells inside this row, multiple bits, let's say. Now, if you want to read some other row, some other cells in some other row, you need to apply low voltage to this. This thing is, okay, I'm going to use this one because there's too much. Maybe we should set this up in a different way later, not right now, yeah. Basically, if you keep doing this repeatedly, activate pre-charge. Pre-charge is the specific name of deactivating a row. Activate pre-charge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, enough times. Before the cells get refreshed, it turns out some vulnerable cells in adjacent rows get flipped because with every activation, they lose charge little by little. And if you do enough activations before the cells get refreshed, you can deplete the charge. And as a result, you get silent data corruption, meaning you cannot read the data that you wrote to that cell. And that's the problem, basically. This should not be happening, but this is already happening because cells are too small and cells are too close to each other. Right? They're affecting each other through noise mechanisms that we're not going to go into. It's a device level mechanism, and their device level works on this topic. Now, the problem is, because we want more capacity in memory to cater to data-intensive workloads, we want smaller cells. And technology scaling enables us to reduce the size of the cell and make the cells closer to each other. And this is bad for this sort of errors, because as the cell size reduces, as the cells become closer to each other, both the charge in the cell reduces as well as the noise increases. And as a result, this problem becomes much worse. I call it read disturbance because there are multiple read disturbance mechanisms. But essentially, the number of activations to induce a bit flip has reduced by more than 100x in some cases over the course of 10 years. We did initial RowHammer studies in 2012. And if you look at 2023, this number has reduced a lot. Okay, this is the original RowHammer paper, which you may have seen, especially if you've taken DDCA. And people have actually, this is a robustness problem. Essentially, it affects your reliability, it affects your safety, it affects your security, it affects your availability, everything. But especially the security community have taken a special interest in this. Yes?
So when you first access something from that row, basically all of that data from the DRAM should have been fetched into a cache. And then the second access should have gone through the cache instead of the DRAM.
Yeah.
Then how would this
Yeah. So not all of your data is fetched. So because a row is, let's say, 8 kilobytes or 16 kilobytes, and normally caching is done at 64-byte granularity, right? So that's one answer. But even if you cache everything, people find, especially you use the word attack, meaning if your mindset is of a security person who wants to attack something, you can bypass all of those caching mechanisms. You can evict all of that data. People have developed a lot of clever mechanisms to make sure to still access DRAM, especially if you're attacking. Make sense? You have a very good point. Regular applications may not work as attacks completely, but if you want to construct an attack, it's easy. Okay, it's easy if you know what you're doing. Let me put it that way. It's not easy if you don't know what you're doing. Okay. Okay, so, and people have shown that, security community especially has shown that you can exploit these bit flips, which are actually quite predictable to induce, to take over a system, to read data that you do not have access to break out of virtual machine sandboxes, to corrupt important data in a machine learning model, for example. We can render machine learning inference useless because the accuracy becomes like 10%. You can steal secret data like cryptographic keys that you're not supposed to have any access to, or machine learning model parameters. So basically, people have developed a lot of these attacks, and these attacks keep coming, which is really fascinating to me. The recent Usenix security conference, which was held 1 month ago in August, they had 7 papers on RowHammer. These were attacks. One of the papers showed that you could do these RowHammer attacks on GPUs and actually make AI inference useless on GPUs. It's actually a good system level paper. There are also other papers that are quite interesting. So this is 2025. We wrote the first paper in 2014, and people are still developing new attacks. It's actually interesting to think about, right? So these bit flips are important, but those are not the end. There are many more bit flips that happen. More recently, in 2023, we discovered, well, we actually published this issue at ISCA. We call this row press. Very quickly, it turns out this is a different disturbance mechanism. In RowHammer, if you want to get the bit flips, you basically activate the row at the maximum possible rate. You activate the row, keep it open as minimum as possible allowed by the standard, and then close it, and then you keep doing that repeatedly. Now, if you actually keep the row open a little bit longer, again, allowed by the standard, within the boundaries allowed by the standard, it turns out you can induce bit flips with much fewer activations. So basically, with a smaller number of activations, 1 to 2 order of magnitude smaller number of activations, you can induce these bit flips. It turns out this is a different type of read disturbance mechanism, which was not well known at all when we wrote our paper. This is something that we discovered in the field using our experimental setup, and we had no idea. We had some hypotheses, but we had no idea to prove how this is actually working out, why this is happening. Later, some folks who work at the lower levels of the stack, device level, read our paper, and they actually figured out how this is happening at the device level, and they wrote papers about it. It's actually fascinating to me because normally the way technology develops is very bottom up. What happens is people discover something, some material, let's say. They build devices, and they understand the devices, and then they build circuits, and then they understand circuits, they build logic. Here, in this case, we basically have a phenomenon that no one has documented before, that we discover at the system level. And we basically encourage people to do studies, and they actually figure out what's happening at the lower level. Yes? Question or no? Okay, okay, good. But basically, these are happening in real devices, and these are examples of manufacturers, Samsung, Hynix, Micron. These are the 3 major companies. And you can see that all of them are vulnerable to this sort of effects. Okay, so why am I telling you all of this in a memory-centric computing lecture? Because the solution to this problem is really being more memory-centric. If this was a RowHammer lecture, I would give you 10 different solutions to this problem. The key solution is really designing better controllers who can anticipate these problems and prevent them from happening. Because the devices are not going to prevent them easily unless you go to a different type of material, etc. Okay, so we've argued for this many years, even before we wrote our RowHammer paper. This was 2013. I was invited to write a paper and give a presentation at the International Memory Workshop. And we basically argued that we're going to have a lot more problems with memory technology scaling. We should design things from a more systems perspective, meaning design controllers that fix the problems. And more recently, I was invited to go to Monterey again, which is a great place to go and present papers at. And this is a great conference also. Basically, we argued that the problem is becoming even worse. It's become even worse in the course of the last 12 years. We should do more. Now, the good news is, over the course of 12 years, something has happened. And industry has finally, let's say, seen the light, and they're doing something in the right direction. Of course, it can be done better. And they're essentially adding intelligent controllers inside the DRAM chips. This is a paper by SK Hynix, which is one of the major manufacturers, almost the top manufacturer today because they've been doing HBM in a good way. Are they better than Samsung these days? Okay, yeah. Do they have a bigger market share? HBM, yes, okay, but not the general DRAM probably. Okay, but basically in this ISSCC paper, they described, this is the first paper where they publicly acknowledged, any DRAM manufacturer publicly acknowledged the RowHammer problem. Interestingly, without citing our original RowHammer paper. They cited some of our later papers, but they didn't cite the original paper. That's good. I mean, that's in a sense, well, it's not good from a scientific perspective, but it's good that if the RowHammer is a household name, right? So everybody just talks about it. Okay, but anyway, they actually proposed some solutions to it. And these are solutions, variants of solutions that we have proposed in our original paper. I don't believe that this is the best solution to this problem, but it's a solution with the right direction, meaning more memory-centric. But it's not completely memory-centric, as we will see. Basically, the idea is having an intelligent controller inside the DRAM chip. If the DRAM chip gets an activation, you have a row, you have an activation counter associated with each row. So you waste some space in DRAM to store the activation counters. And with every activation, the DRAM chip automatically increments the counter associated with that row. And at some point, if the activation count is greater than some threshold, which they don't disclose, of course, or they don't disclose how to calculate, of course, and the DRAM chip takes an action, which is refreshing adjacent rows. They don't talk about how many adjacent rows, etc. So these things matter. That's important. But the key thing is there's an intelligent controller inside the DRAM chip that's doing this. Now, it's not completely independent. That's the downside, because the memory controller still needs to issue some commands. Memory controller on the processor chip needs to issue some commands to make this happen. Okay, so this was standardized by JEDEC in 2024. and it's going to be implemented in all DRAM chips going into the future. This is actually fascinating and interesting because this is, as some folks in industry have said, this is probably the biggest change that has happened to DRAM in the last 20, 30 years. That's fascinating, right? This is an area where no change should happen from the perspective of industry. They're very happy if no change happens, but they had to do this, right? Okay, I like it because this is something that we argued for many years, right? And this is the right thing to do, I think, but we can do better. So the question is, of course, are solutions good, right? This is one solution to a problem. You can guess what the problem may be, but it's not a good solution, as you can see, right? If you throw this picture to a 10-year-old kid, they will tell you it's a terrible solution. If you throw this picture to a 90-year-old kid, they will also tell you it's a terrible solution, hopefully. Yeah. So we keep evaluating industry solutions, and we have papers on this topic that I'm not going to discuss, but in general, solutions become better if the controllers are more intelligent on the memory side. So you need to be much more memory-centric. Okay, so I'm going to mention one more memory-centric way of thinking about memory. We call this self-managing DRAM. And one of the major issues today is memory DRAM, for example, is a complete slave to a processor. You have a processor, memory cannot do anything by itself. Processor has to dictate things, right? Meaning, if the memory cannot even refresh itself, there's a data retention problem with memory. And unless the processor says refresh, the memory cannot refresh things internally, which is interesting, right? So memory has no autonomy. And this is a very, if you think about this, this is because we have a very processor-centric mindset, right? Why shouldn't the memory do operations by itself? Well, because we're very processor-centric. And you can accept this as a fact and move on. We don't accept this fact as a move on. Can we do better, right? That's a good question. And if you look at this, I think we can do better. We can be a little bit more memory-centric. We can enable DRAM to have some breathing room so that it can do some maintenance operations like RowHammer mitigation, updating those counters so that they have, memory has enough time to update those counters and make a decision. Should I actually refresh the adjacent rows so that actually I prevent RowHammer, right? And to enable this, we propose a very simple modification. We don't want to modify the standard much. We don't want to expose internal proprietary information, but we want to give the freedom to the DRAM chip so that the DRAM chip can say no to the memory controller. So a memory controller says, activate this row. DRAM chip says, sorry, memory controller, I'm not going to obey you this time because I'm doing something as important as what you're trying to do. I'm trying to protect things for RowHammer, right? I'm trying to protect this region. It doesn't need to be the entire DRAM chip, right? It can be this region that you're trying to access. I'm doing some refresh operation. I'm doing some scrubbing. I'm doing some processing operation over here, right? And I'm as important as you. Hopefully this makes sense, right? So there's a NAC, negative acknowledgement. And we believe this is a step toward the right direction, a little bit more memory-centric, not completely memory-centric, but a little bit more memory-centric, as opposed to being completely processor-dominated on the memory. And this enables a lot of breathing room and partitions that work nicely between the memory controller and the DRAM chip. Memory controller does what it's good at, orchestrating access operations. DRAM chip does what it's good at, maintaining itself, refreshing, figuring out what to refresh, what not to refresh, right? Today, you cannot innovate inside the memory space that much because you have to change the interface. You have to change the memory controller if you want to do something in the memory chip, because everything that you want to do that's innovative in the DRAM chip requires a change to the memory controller. That memory controller is designed by someone else. They don't want to do that. And that interface is a horrible thing to change. Like that change in RowHammer took at least 12 years to happen, for example. If you want to change that interface, you need to convince 390 other companies that are in this political standards body called JEDEC. So it's a mess. So this is a very simple idea, I think, that is in the right direction. But it turns out to be so controversial that it was rejected 6 times by major conferences. But we wear these rejections as a badge of honor. That means we're doing something right, that if people are actually so afraid of a simple idea like this, right? Anyway, it hurts if you're the graduate student who's writing the paper, but it also builds character. Okay, the key is basically, you may have a great idea, and it may make sense to do it, but the world may not operate that way. The world is still very processor-centric, right? So you need to be very resilient. Okay, so we've shown in this paper that you can actually implement many different things inside DRAM if you actually have this sort of interface. And if you're more interested in more, this was part of Hassan's thesis, but it was published 2 years after he defended his thesis, which is also interesting. Okay, that's self-managing DRAM, which is also interesting because somebody who reviewed this paper said that this is a very disruptive idea, which I don't think it is, actually. It's just a slight movement to be more memory-centric. But if you're processor-centric, I guess it becomes extremely disruptive because it challenges your worldview, right? How can memory do some things by itself? Okay, it's good to have some fun in research too, right? You don't always take the negative reviewer comments seriously. Okay, so I think there's a lot more to come in this area, which is also fascinating. So we do a lot of studies in our lab. We found out that RowHammer becomes worse with aging. And this worries me a lot. We don't quite understand aging of hardware yet. And if you actually take hardware to space, for example, or take it to harsh conditions, extreme conditions, to oceans, etc., hopefully for good reasons, not bad reasons, is this going to survive there, right? Especially cutting edge hardware. Okay, so we have some works in this area. More recently, we also discovered that there's some phenomenon called variable read disturbance. I think of this like quantum-like effects that affect what we have. Essentially, the read disturbance threshold, how many activations you need to perform to induce a bit flip, changes randomly, unpredictably over time. So you may be able to induce a bit flip after 10,000 activations today. Tomorrow, you test the chip, you can induce a bit flip after 1,000 activations. Next day, 100 activations. So basically, you don't know how to optimize the solution, right? Because you cannot say n activations, a fixed n activations will solve your problem, right? This thing changes. So it's fascinating also, which means that you need to have even more intelligent controller, right? A controller that really understands what's going on, different characteristics, temperature, etc., and how this read disturbance threshold changes and adapts its mitigation strategies to it. Okay. So this appears at HPCA, and there's more waiting to be discovered in this area. This is fascinating. This is also another example of a read disturbance mechanism where there's absolutely no documentation of it anywhere that we looked. So people don't know about this at device level, and we're talking with device level folks to really understand it at the very low levels, why it's happening. Okay. You may say, okay, what about other technologies? I'm not going to focus a lot on other technologies than DRAM. I'm going to talk a little bit about flash later on, but emerging memory technologies also have problems, and they require intelligent controllers. We've done a lot of work on phase change memory, STT-MRAM. These are emerging, and they're still emerging. We'll see if they emerge at some point, really, at a large scale at least. But these technologies usually have problems that are even worse than DRAM. Like phase change memory, for example, has the endurance problem, meaning if you write to a cell, you degrade the cell. So you only can do a limited number of writes to a cell, let's say 10,000 times, which means that you immediately need to have an intelligent controller to make sure that if you do more writes, or if you're about to do more writes, you do something to remap the data, for example, right? That's one idea. So without an intelligent controller, you cannot really get away. And also, even if these technologies don't have this sort of problems immediately, none of these technologies have scaled to the dimensions that we've scaled DRAM into today. DRAM is actually at a very special place. It's technology scaling. It's less than 10 nanometers almost today, for some dimensions at least. And if these technologies scale and they're tested at that level, I believe they're going to have a lot of issues, actually, knowing what I know about these technologies. Plus, I think there's also something that's very fundamental to any technology. As things scale to very small dimensions, they start to break. Because we're really dealing with angstroms of things right now. And if your computation unit or data storage unit is that small, then they're going to break, under some conditions at least. And you cannot possibly test all possible conditions in the world, let alone space or oceans, etc. Right? Okay, so it's good to think about that way. That's why we keep investing more into our laboratory for understanding memory. Making Xilinx happy by buying a lot of FPGAs, unfortunately. They could be more generous by donating a lot more FPGAs. And the good news is there's a lot more awareness of these problems in conferences today, and also industry, as I said. When we first wrote our RowHammer paper in 2013, it was rejected from the micro conference. Some people argued this is not an important problem. Some people argued that this is not a problem for us big computer architects. You should publish this at some low-level conference or somewhere. The good news is everybody's, at least conferences are having papers, top conferences are having papers on these topics. In fact, some multiple sessions on RowHammer today. It's fun to see this. Like, it's good to have this perspective, right, of 12 years. That's why we are, when you do the research, it's more of a long-term effort. You may not really be able to convince people, even if you publish a paper immediately. But over time, if the problem that you're working on is real, and if you actually do a good job in studying that problem and demonstrating it and providing solutions to it, people will come around, right? Long-term is better than short-term. Whereas if you do something short-term, it may be useful in the short term, but it may be useless 10 years, 20 years down the road, right? It's good to think about research that way. What is the fundamental thing that I can do that can have much larger impact, right? Okay. And this was the DRAM-Sec workshop that we organized with ISCA 2025 this year. If people are interested in this workshop, we have a YouTube video of the entire workshop, including the panel, where a lot of people from industry fought with each other on how to solve RowHammer. Fought is a strong word, of course, but they kind of argued with each other. Normally, you don't see these arguments in public. Okay, any questions? Is this interesting? Okay, that's good. Then I'm going to continue. So now, that was one perspective, right? The technology scaling perspective. Now we're going to take the application and system scaling perspective and try to accelerate applications. I'm going to define two terms. The terminology in this field is a mess. Processing in memory is what I'm going to use for the general concept of doing computation in memory, essentially. But there are two different types of it from a fundamental nature of computation perspective. How do you treat logic, essentially? They differ in how they treat logic. So today, you design logic, and you have a logic design flow that you have gone through in DDCA, for example. And you fabricate logic in some technologies, and that logic fabrication is usually very different from how you do memory fabrication, especially DRAM or flash type of fabrication. So today you design memory and logic completely separately, right? There is a memory design process, memory fabrication process, completely different from logic design and logic application process. Of course, SRAM is different, right? SRAM is more like the logic type of memory that is compatible with logic design. And if you think about DDCA, flip-flops are essentially logic used to implement memory. But essentially, you design logic and memory separately, and you put logic far away from memory today. Main memory, DRAM, is separate from logic. Processing near memory says, put it closer and closer and closer. Put the logic inside the DRAM chip, for example, next to the DRAM bank, inside a logic layer underneath memory layers with 3D stacking technologies, integration technologies. Put it in the memory controller, right? At least the memory controller, that's not too far from memory, right? It's still far, but not too far. So that's processing near memory. Logic and memory are designed separately, but they're close to each other. Processing using memory is fundamentally different. You have logic, forget about logic. You don't have logic. You have memory. What can you do with this memory? Exploit the fundamental operational principles of this memory circuitry, which are fundamentally analog in nature, to actually also do computation. This is fascinating. And any memory technology has some fundamental properties that you can use to do computation. And different memories have different types of properties that enable different types of computation. This was much less well known until 2010s. We did some of the original work in DRAM, but there were other works in memristors, for example, that also showed similar things around the same time. That you can do different types of computation by exploiting this analog operational properties. So I'm going to talk about that too. This is much longer term, but it's much more fundamentally energy efficient, in my opinion. Processing near memory is shorter term. It still has some challenges, but you can do much more complicated things if you actually design logic next to memory. Does that make sense? I think in the end, we need to combine both. So I'm going to skip the slide. But today, there's a better mindset than, let's say, 10 years ago when we were doing some of these works that I'm going to talk about. Today, there are a lot of companies that are actually designing memory chips that can do computation. So this UpMem company, whom we worked with a lot, they were more recently bought by Qualcomm. Maybe unfortunately, maybe fortunately. Unfortunately, because we cannot work with them anymore, because Qualcomm is not an easy company to work with. Fortunately, because maybe Qualcomm will do the right thing and put some of these things in their chips in a better way. Let's see. But essentially, what this company did was they put processors inside the DRAM chips, and we have a lot of papers that I'm not going to talk about in this lecture that evaluates it. Samsung, SK Hynix, and Alibaba, they all produce DRAM chips that are internal use for them at this point, I think, where they can do computation next to each bank. Samsung and Meta have designed this boards where you have an FPGA next to a lot of memory. You can do recommendation model acceleration. So these are more specialized accelerators over here, and this is a more general purpose processor next to each DRAM bank. There are also some other things that I'm not going to talk about at all. But I'm going to start with this emerging memory technology, which is 3D stacking, which we have done a lot of work on that I'm going to talk about soon. But processing in memory landscape today is also good because there are some interfaces like Compute Express Link that enable offloading of computation from the processor more easily. Again, you need to know the details, but there are some papers that you can read. This is a paper from SK Hynix, for example, that shows that by offloading computation to an FPGA next to a lot of memory, you can accelerate databases. Samsung also has similar papers. Let me give you some examples of the type of benefits that you can get from our own, let's say, research. We were very interested in 3D stacking technology in, I don't want to call it relatively early days, but relatively early days of 3D stacking technology where things were not mature. Today, things are much more mature, but there's also much more maturity that needs to be developed to be more truly 3D stacked. So what is 3D stacking? You can essentially stack memory layers on top of each other, and you can stack a logic layer underneath. And this logic layer can be connected to memory layers through some interconnects. And this interconnect enables you to access the memory fast, low latency, high bandwidth, low energy, compared to having larger interconnects to connect to memory through a CPU, for example. And in this logic layer, assuming this logic layer can be done really well using the logic process, you can actually put any type of logic over here. That's the good part. Of course, the benefits of this technology depends on how many of these interconnects you can put, how reliable they are, how thin they can be. So the bandwidth benefits are depend on that. And going forward, there are better technologies that could be developed. Hybrid bonding is happening, for example, where you can have a lot of these interconnects that are smaller. But with monolithic 3D integration, which is a fabrication technology, maybe you can have even better interconnects between these layers. So there's a lot of technology that's happening. So what we did was not any of that technology. We trusted, we believed in the technology. And we said that, what can we do with the technology, assuming this 3D stacking becomes real at some point? And our goal was to accelerate important applications. So we did everything in simulation. This is a full system level paper, simulation paper, which we published at ISCA 2015. And you can see that we're starting with the space. In the logic layer, we put a lot of in-order cores to do computation. They're interconnected with each other with some network. And essentially, these in-order cores communicate with each other so that they can do some sort of computation. Now, we're very interested in graph processing, graph analytics, for example. Page rank computation, for example, is a graph computation to rank pages on the internet. What we did in this work is to actually ship computation to the data. So whenever you partition the graph node across these cores in some way, hopefully in a good way, so that you can exploit locality in each core as much as possible. And if you want to update a graph node, you don't bring the data from the remote place. You send the function to the core that actually hosts the graph node that you're trying to update. You basically ship the function to the data as opposed to data to function. Yes?
What does in order stand for?
Oh, in order. You took DDCA, right? Okay, in order execution versus out of order execution. Yes, that is the in order here. Basically, these are very simple cores. And there are reasons for it, because if you actually put complicated cores, they consume a lot of power. And one of the issues with 3D stacking technology is thermal. Heat, it doesn't have any place to escape. So your thermal capacity is, let's say, restricted. That's why we cannot put expensive cores over there. But if they're really simple cores, you can put many of them. Okay. Yeah. Well, interposers, you can do that, but still it's a different interconnect, right? It's not true 3D stacking. With true 3D stacking, you can do it. The problem is what kind of logic can you put over there, right? Modern HBMs, at least so far, don't have, they fabricate the logic using a DRAM process. As a result, your logic sucks. Meaning in terms of the size of the logic, it's huge. You cannot clock it very high. And also, leakage is bad. Now, if you actually believe in the technology and put a good logic layer over there, which is fabricating the logic process, and it can connect things nicely, which is hopefully going to happen in HBM4, that's in plans for HBM4, then I think a lot of things can be done, right? That's the goal.
Doesn't it worth it by exploring that even though we have some like this overhead of DRAM technology, we still kind of prove that it could be useful in some scenarios?
Yeah, certainly. I mean, you can do that, and there are works that did that. For example, I think Samsung's HBM PIM has a bad logic layer, and they still show some benefits in their works. Yeah. So our assumption was a better logic layer at the time because we believed in the technology, and I don't like the arguments that it cannot be done today, so we should assume a bad logic layer. I prefer what could we do if we actually have a good logic layer? That was what we did in our work. And essentially, we accelerated graph processing. Okay, I've given you the basic ideas, but this is not enough. What you need to do is actually interconnect these devices because the memory that you have over here is small, right? If you really want to deal with large-scale graphs, you really need to interconnect many of these devices. So basically, you have a distributed accelerator that you can offload computation into. Okay. So I already said this, and I'm going to skip the prefetching because we don't have time. But basically, Tesseract, the system we called at the time, we're talking about 12 years ago. This paper was rejected twice also before it was accepted to ISCA. It looked like this. So essentially, with 512 in-order cores, you have access to 8 terabytes per second bandwidth. And these are the processor-centric systems that we compared to. They cannot achieve that level of bandwidth available to the cores. And I kind of like this picture because this kind of resembles how we build GPUs today. GPUs are like this, except they're not near memory as much. They have, if you look at GPUs, each of them look like this, but then there's a memory attached to it. And that's HBM, which is interesting. So we should have looked at machine learning. So this is a good system for accelerating machine learning. Okay, so you get significant benefits in terms of performance and energy on many real workloads that we examined. I'm not going to go through this. There are a lot of papers that built on this. They actually increased the benefits. They fixed some of the problems that we couldn't solve for some reason or other. They optimized for graph processing. And in the end, they showed that you could go up to 100x performance improvement and 100x energy reduction, which is actually quite significant because you're improving performance and energy at the same time, right? That's not a trade-off. And people, even though they originally rejected our paper multiple times, they decide, oh, it was actually an important paper. So they included in this 50-year issue of ISCA. But so again, time heals a lot of issues, let's say. So if you're rejected today, think 20 years down the road. Okay. I'm going to skip some of these things because we don't have a lot of time, but you can actually do even more if you can optimize your algorithms at the high level to the hardware and change the ISA. If you actually are even more aggressive in changing the system stack, you can get even better performance and energy improvements. I'm going to talk about machine learning inference a little bit. This is the work that I mentioned that we did with Google. We spent some time with Google analyzing their neural network models on the Edge TPU. This is their Edge machine learning accelerator at the time. And we found out that there is a lot of heterogeneity in the models. So different layers from different types of models have different characteristics essentially. And I'm examining arithmetic intensity on the y-axis here, floating point operations per byte that's fetched from memory, and the parameter footprint. What is the input parameter size to a layer? And you can see that these layers over here, they have huge arithmetic intensity. You do a lot of operations on a given byte that you fetch, and your input set size is very small. And here, there are some layers that do, in fact, less than 1 operation per byte that you fetch, and the parameter size are huge. And we concluded that it doesn't make sense to design a single accelerator that tries to cater for all of these different characteristics. Let's design something much more heterogeneous. And then we analyze within each model the characteristics, and you can see that different layers in each model also have significant variation. as up to like 200x or 244x in terms of arithmetic intensity and operational intensity. So this is the idea basically. Instead of designing a monolithic accelerator that tries to cater for all of these different characteristics, both compute-intensive parts and memory-intensive parts, let's design different accelerators that cater for different families of characteristics. Again, in our work, we've designed 3 of these accelerators. One of them is very similar to HTPU, but much more leaner because it doesn't need to deal with the memory-heavy parts of the neural networks. It deals with the compute-intensive parts. So it's actually similar to the HTPU. But then we put 2 different types of accelerators in the 3D stack DRAM in the logic layer. Again, we assume a good logic layer. And we have 2 different types of accelerators such that they cater to different types of characteristics. And again, there's a lot of detail over here that I'm skipping. You need to characterize what kind of layers go to what kind of processors or accelerators. And this can be done statically or dynamically, meaning there needs to be a runtime scheduler over here that decides what layer gets executed where. So the system is overall more complex because whenever you want to exploit heterogeneity, you have more complexity in the system. But the execution is much more efficient in terms of both performance and energy. And we see significant benefits, like on average 3x compared to the baseline HTPU, and in terms of both performance and throughput. Yes?
The benefit is that we can keep our algorithms, right?
Yes, you keep your algorithms, exactly. You don't change algorithms in this particular case. That's a very good point also. But that said, maybe you can design better algorithms given this hardware, right? Because clearly those algorithms were designed with GPUs in mind and then later TPUs in mind. And we didn't change the algorithms to match the existing hardware. So we could even do better, but we didn't go there. Yeah. Yes.
How does the latency look like for a logic unit to access data from the same column when compared to, let's say, GPU's logic unit accessing data from registers or shared memory?
Yeah.
How does it look like? How does both of those latencies?
Yeah. So that's a very good question. So if it's longer on the memory side, because if you actually are accessing things on the memory side, you have longer access. But we do actually have some buffers in the logic layer. So we don't eliminate all of the buffers. So these accelerators over here, and also in other works, they have some buffer, as you can see. So that latency is very similar to how GPU accesses. Makes sense, right? We don't go to memory for every single operation. We buffer things, and that locality is extremely important to exploit, even if you're doing things close to memory.
Yeah, because I was thinking if there is any case where the traditional thing would be better than this. But I think introducing a buffer would solve that problem.
Exactly.
But isn't this again making a bit similar to how caches are placed? Like, is
Yeah.
the buffer sort of a cache?
It is a cache in the end, but it's a much smaller cache. So in all our works, basically, we have this buffer, but it can be much, much smaller. You don't need to have 32 megabytes of caches, basically. You can see that I don't remember the exact numbers over here, but they're much smaller. So even this parameter buffer over here in the monolithic accelerator is much larger than any of these buffers combined. Yeah. So you can optimize the entire system that way. Yeah. But that's a very good question, basically. Okay. Okay. So there's more in this paper, if you're interested, which is actually interesting to read, I think. So we did more work, but I'm not going to talk about. There's a lot of evidence that you can actually accelerate applications and make them more efficient by doing processing near memory without changing applications. So you can see that this neural network example, as you said, you don't change the workloads. You basically offload things at a layer level. Here, you offload things at a function level. So these are easier to adopt than designing a system like TCuARCH where you change a lot, right? We've done a lot of work on genomics. That again, genomics is a very good fit actually for processing near memory because it doesn't require heavy computation. It requires a lot of bitwise operations, for example, and bitwise operations are relatively easy to accelerate near memory. In fact, we've done work on genomics in real UpMem devices, and we see significant performance improvements compared to existing CPUs and GPUs, etc. So genomics or bioinformatics algorithms are actually a good fit. More recently, we've been looking at in-storage processing. I will not have time to talk about it, but if you are interested, you can talk to that person over there, Nika. You can raise your hand. She's been doing a lot of work on storage-centric computing. Here, the reason is the data sets are huge. And in my opinion, storage is a place where you can do a lot of computation because it already has a lot of processors. Why not add more processors over there? Why add computation capability to do more computation? For example, in metagenomics, you take a sample from your environment. It could be this thing over here. And you basically try to figure out what's going on in my coffee, right? You may not want to figure that out. But if you decide to figure that out, what you do is you basically sample things. There are some sequences that come out of the nanopore sequencing machine, for example, and then you compare it to many, many databases of reference genomes. It could be hundreds of terabytes, right? And this is clearly a hugely data-intensive problem. And this is useful for example, outbreak prediction, right? When you, this may enable you to predict some outbreaks early on if you actually do the sampling frequently at critical places, right? It's good to think about that, right? Maybe my coffee is not that interesting, but outbreak prediction is a little bit more interesting, right? So this is very storage intensive. So that's why doing things in storage makes a lot of sense. And we do more things in storage, and you can talk to Konstantina about that. She's hiding in the back over there. Okay, so we have more works, but I'm not going to talk about that. Andreas can tell you about the RICE work that accelerates retrieval. And some of these papers, actually, you can select. Some of these, actually, we have included in the list. There are many more examples over here that we don't have time to talk about. Let me see how much time we have. Sorry, I didn't give you a break, but I really want to finish today. Next time, you'll have a lot of breaks. Hopefully, this is interesting. It's worth staying for. Okay, more recently, we've shown that you can actually accelerate LLMs very quickly. The basic ideas, actually, fundamental principles are very similar. I'm going to talk about this PAPI system. The idea is there are different parts of the workload that should be accelerated in different ways. Instead of having a single monolithic compute-centric accelerator, have different types of accelerators. Some of them are compute-centric, like how we do acceleration today. Some of them are near-memory accelerators, and figure out what parts of the workload should be accelerated where. And if you do that nicely, you get significant performance energy benefits. For example, in many machine learning models today, or LLMs, you have some fully connected layers that are extremely compute-intensive. They should be executed in a CPU or GPU, right? Because they're extremely memory-intensive, extremely compute-intensive. The arithmetic intensity is high, etc. But there are some fully connected layers that are not as compute intensive. They could benefit from near memory processing. They're still compute intensive, so you should put a lot of units next to each bank. But this is how you actually, this is what's better than actually purely compute centric. And there are some layers that are extremely memory intensive in terms of both capacity and the bandwidth requirements, and they're not that compute intensive. And you design another near memory processor for it that has less computation capability and thus less expensive, right? So this is an example, right? That's the idea. Now, of course, the question is, how do you realize this? It's easier to simulate than do it. So it's good to think about what kind of research needs to go into it. I think we need to actually have more configurable near memory processing units to realize this sort of ideas. Okay, in this other work, we've actually looked at, can you eliminate GPUs or TPUs in the system? And we show that you can actually do that, and you can get a lot better cost efficiency if you actually design a system for LLM inference to be near memory. And I'll let you read the paper if you're interested. This could be one of the papers that are actually already on the list. In the remaining part, unless there are questions, I'm going to focus on something more forward-looking, let's say, more difficult in many ways, multiple different ways, but a bit more fascinating. I'm not saying the previous one is not fascinating. It's still fascinating, and it still has a lot of problems, but this is a little bit more fascinating because it's much less well studied. And that's the idea of processing using memory. How do I take advantage of the fundamental operational characteristics of a memory device to do computation? So I'm going to focus on processing using DRAM, and this is an area where we've done a lot of work on. And I'm going to give you a lot of examples of what DRAM can do. It can do bulk bitwise copying, initialization. Maybe boring, but a lot of workloads actually do that. It can do functionally complete, Boolean complete, if you remember from DDCA operations, and or not, majority nor NAND. It can generate true random numbers. It can do more complex computation using lookup tables. I'm not going to talk about everything because we don't have time. But most of these, not all of these, can be done at low cost, small modifications to the devices. And the idea is to take advantage of the analog computation capability of DRAM internally, but meaning charge sharing capability. But there's also sense amplification capability that's there in DRAM that actually amplifies the analog signal quickly back to a digital signal. The fundamental idea is actually very simple. Activating multiple rows, either sequentially or concurrently, performs either data movement or computation. If you do it sequentially, you move data. If you do it concurrently, you do computation. That's the idea. And what's fascinating is you can see all of these functions even in commodity off-the-shelf DRAM chips. So with our infrastructure, you can violate some timing parameters, you can abuse the DRAM chips, and you can actually see these functions. Meaning, even though DRAM is not designed for any of these purposes that we envisioned it for, existing DRAM devices, without any change to the DRAM device, without any change to the interface, just changing the memory controller with an FPGA, of course, you can actually do all of these, which is fascinating, right? And because we showed that you can actually do all of these, a lot of memory companies got excited. Oh, can we actually do this? Right. So we're actually working with some of them to do this. But I think it's not a shorter term thing. It's a longer term, because there are a lot of issues in this sort of analog type of computation, even though analog may be limited for a short duration. But we can actually get significant energy and performance improvements, much more significant than what we see with near memory computation, assuming you can fit your algorithms nicely to this sort of execution model. So there's another assumption over here. Okay, let's get some examples over here. So we're going to start with data copy and initialization. This actually, we do a lot of copying of data. Imagine initializing a 10 terabyte database. You basically go write zeros everywhere or some random number, which is a waste of time, essentially. So the question is, can we do better? Google, in their study that I mentioned at the beginning of this lecture, they basically analyzed their workloads, and they found out that only 2 function calls, these are not all of the data movement, not all of the data copying initialization, the memmove and memcopy occupies 5% of the execution cycles in their entire data center workload suite. That's a huge number for 2 function calls, right? Imagine like people are writing millions of function calls. Only 2 of them is responsible for 5%. Right? Okay, so how do we do the data copy today? Essentially, if you want to copy, let's say, and also in their paper, I should say that, in their paper they say the approaches like what I'm going to describe soon, row clone, because our paper was published earlier, are going to be more important into the future, and that should be investigated more and more. That was nice of Google. Sometimes companies can be nice also, not always. Okay, but basically, how do we do data copying? Let's take a look at bulk data copying. There are solutions to smaller data copying also, but if you want to copy this white page, let's say 4 kilobytes, to this gray page, another 4 kilobytes, how do you do it today? Basically, you have to go through the processor today because there's no computation capability on the memory side, right? You have to at least go through the memory controller through the DMA engine. Basically, you bring the source page byte by byte all the way into the L1 cache and the registers. You bring the destination page, do the write, and then write back the destination page. That's 12 kilobytes of data movement, and it's basically occupying the memory bus a lot, right? Okay, again, let's take the perspective of a 10-year-old kid. We didn't actually get back to that person a lot, but this is a good time to get back to that person. Describe that system to your 10-year-old kid. Tell them this white page and the gray page are very close to each other in memory. In fact, they may be in the same subarray. And I'm doing this. Am I doing the right thing? That person will be very honest with you, and they will say, go and design something else. Why don't you just do this? Right. That sounds good, right? You disagree with the 10-year-old kid? Okay, yeah.
The reason why we do it this way is because the CPU is the only
yes.
that can actually perform the write.
Exactly. Yeah. Or perform anything, basically. Do any type of, yeah, exactly. Any type of modification of data. Yes, that's true. Yeah. Yes, go ahead.
Are there also like DMA engines closer to the memory?
Yes, that's right. That's what I meant by you can do it through the memory control, but you still go through the bus over there. Yes. So if you're smart, you can do it through the memory control. You don't disturb the L1, L2, L3, but then you need to go through some setup overhead, etc. Yeah. Okay. So you guys want to be 10-year-old kids. Good. Okay. So basically, I think we should be thinking like 10-year-old kids so that we don't have all of these problems. And I will go through this. And if you're actually design something, in the best case, you can reduce the copy latency by more than an order of magnitude, and copy energy spent on the memory side by almost 2 orders of magnitude. I'm going to give you an example of how we do it. And this is the best way we could find out so far. Maybe there's a better way, unlikely in the current structure of DRAM at least. But the idea is you have these DRAM rows, DRAM subarray, and there's a row buffer, which is sense amplifiers. We're going to exploit the chart sharing properties of how we access DRAM. So if you want to access one row, you activate the source row, which brings the data into the row buffer. Now the data of that row is strong in the sense amplifier. Sense amplifiers are essentially SRAM structures next to DRAM that have amplified the data. Now the second step, if you want to copy this row to some other row in the same subarray, you implicitly you activate the destination row, which implicitly deactivates the source row and connects the sense amplifiers to the destination row. So you basically use the sense amplifiers or the row buffer as a temporary storage to move the data from the source row to the destination row. That's the idea. Very simple idea. We call it row clone. And in the original paper, to do it reliably, we added some hardware, but it's negligible hardware cost to do it in the same subarray. And we see significant performance energy benefits. Okay, there are other data movements that you have that may not be in the same subarray. This is the best case. There are other solutions to it that I'm not going to go over in this talk, but there's work in that area also. This is the original paper. It was also rejected once by ISCA. I guess they didn't find it interesting enough. But I think it does the right thing. Okay, let me give you how to do computation, and then we're going to talk about how you can do this in real devices. So it turns out, okay, maybe I'll talk about how to do it in real device. It turns out basically what we're doing is 2 consecutive activates, right? Activate, and then activate. Now, if you violate the activate timing parameter in DRAM, in existing DRAM devices, in almost all DRAM chips, you can see this happening. So basically, you don't obey what the DRAM manufacturers tell you in the data sheets. You say, I'm going to try to do this. I'm going to map to the same subarray a source row and a destination row. And I'm going to see if this copy is really happening. And I'm going to violate the activate to activate timing parameter such that hopefully I will see this behavior. And you see this behavior almost perfectly reliably in real DRAM chips, which shows that even if you do nothing today to the DRAM chip, you can actually do this sort of data movements, right? Now, imagine what you can do if you actually go and say, oh, I want to design this chip to do this reliably, right? So the mindset, if the mindset changes, you can do a lot. Okay, I'm going to show you those results, but if you don't have time, now you know those results, basically. Okay, let me talk about computation. This is a little bit harder, but it's also fascinating, and it's also based on the chart sharing characteristics. Now I'm showing you 3 rows in the same subarray, but instead of showing the entire rows, I'm showing you 1 cell each in each row. Imagine you have 4 kilobytes of cells or 8 kilobytes, whatever your row size is. And you can see the capacitor, you can see the access transistor, you can see the bit line that they're connected to. You can see the sense amplifier, which looks like an SRAM circuit, cross-coupled inverter, and 2 cross-coupled inverters. And you can see the other end of the bit line, which is connected to some other subarray normally. But basically, if we had the primitive to concurrently activate these 3 rows, you would get a function. If you concurrently activate these 3 rows, based on the chart sharing principles, if at least 2 of these cells are charged, this bit line would be perturbed toward the charge state, and eventually the sense amplifier would kick in and amplify the data to the charged state. So if at least 2 of these cells are charged, you get the charge state at the end in the bit line and all of the cells. If at least 2 of these cells are discharged, you get the discharge state at the end. And that's a bitwise majority function. Right? At least 2 of 3 is bitwise majority. Right? Now you can do bitwise majority computation across the entire row, 8 kilobytes. That sounds good, right? But bitwise majority is special because if you set C to 1, you get the OR of A and B. If you set C to 0, you get the end of A and B. Now you have bitwise OR, bitwise AND. Sounds great. I'm missing a NOT to be Boolean complete, functionally complete, right? But NOT is already there, actually, except it's in the wrong side. So if you actually activate C by itself, you get the complement of the C on the other end of the sense amplifier, right? Because you have an inverter that's already there. That's there for sense amplification purposes. And the NOT is already there. You just need to feed it back into this array. And in our original paper, we proposed an expensive method for doing so, but there are other methods for doing it relatively cheap. Or you need to figure out how to deal with it on the other subarray. So there's still work to be done in this area. But if there's a way to actually feed it back over here, now you have functionally complete execution in a single subarray. And if you have that sort of execution, you can map your algorithms to take advantage of it. Here, you need to change your algorithms to take advantage of it, or maybe you have algorithms that are designed to exploit bitwise operations. You just need to map it to the subarrays so that you can actually take advantage of it. And we did that with the bitweaving database that was developed to maximize bitwise operations so that they can actually accelerate things in a much better way using GPUs. And we find out that you can improve performance and energy significantly. But there are many other algorithms that you can accelerate. You just need to think of your algorithm differently, right? In my opinion, you can accelerate anything with this. And I'm going to show you a mechanism to do that actually soon. But some algorithms are much more, let's say, amenable for acceleration because they're already designed in a block bitwise manner, right? Microsoft, for example, had this Bitfunnel web search engine, which is block bitwise. Encryption algorithms, like homomorphic encryption, is designed very bitwise potentially, and you can take advantage of it, right? Set operations also, okay. Okay, this is the original paper that, actually, we had a shorter paper that introduced partially, but this is the longer version that was also rejected 4 times before it got accepted. It's also interesting. One of the reasons for rejection was, this is a great idea. DRAM manufacturers will never implement it. Reject. That sounds like a terrible reason for rejection from a scientific venue, right? First of all, who cares about DRAM manufacturers implementing it? We're doing science over here. Not every idea has to be implemented, right? That's one reaction. Second of all, which is even worse, is how do you know? Do you have a crystal ball, right? It's good to think about how you review papers, right? So a review of a paper should be scientific and careful as opposed to, oh, I have a gut feeling that this is not good. Yeah. Yeah, unfortunately, the world is such a place where you're governed by some people. I have a gut feeling this is not good for me. You can imagine some people like that. Okay, not gut feeling. It doesn't make money for me, so I don't do it. Or I'm going to do the right thing for how to make money for myself. Okay, anyway, a lot of jokes that I can crack, but at least we shouldn't be doing it in science. But yeah, humans are humans everywhere, so what do I expect? Okay, where are we? Okay, 9 minutes. Okay, so you can make this completely programmable. SIM-DRAM is a work. So I'm going to describe this relatively quickly, but the basic idea is if you have this sort of engine, you can implement any operation on it, any block bitwise operation. So a user can specify any operation they want, however complicated it may be. It may be slow, but it can be implemented. So the idea, for example, it could be a convolution operation, it could be a multiplication, it could be a division, it could be whatever, FFT, right? You specify it like a circuit that looks like this, and or not. And as people who have taken DDCA, you know how to do this, right? Any operation thrown at you, you can design a circuit for it, right? Because you have a Boolean complete system. And we actually converted to a majority inverter graph. It turns out in superconducting logic, majority gates are used a lot. And people have developed electronic design automation tools to optimize those graphs in EPFL. Nani Demicheli's group has done a lot of work on that. And we use those tools to reduce the latency as much as possible and optimize the graph. And then we converted to sequence of DRAM commands, like triple row activation, row clone, etc. So you need to combine all of those commands, and you store that microprogram. We call this a microprogram to execute this desired operation. We store it with this new instruction somewhere in memory. And when the user or the programmer or the compiler incorporates this instruction in the program, and when the system and the CPU executes this instruction gets shipped to the memory controller, which goes to the microprogram and executes these DRAM commands to execute that operation. That's the idea. It's a full framework, end-to-end framework to enable this sort of block bitwise execution. And we see significant benefits. Again, you can read the paper for more detail. More recently, this is SIM-DRAM. More recently, we have looked at some of the downsides of doing computation like this. And one of the downsides is you're always operating at a large granularity, right? 8 kilobytes, let's say. If your row size is 16 kilobytes at a time. But many applications don't have that large vector width. You can think about it like block bitwise parallel. In many cases, you need 512 bits, and you don't need more than that. So what happens in that case, right? You're using only 512 bits. Everything else needs to be zeros, meaning you need to pad your rows. or you cannot do the operation if you don't do the data mapping correctly, right? So in this work, we propose a finer grained DRAM where you can partition or segment the rows to smaller rows. We call the sector DRAM or fine grained DRAM, where you can activate individual mats, and individual mats are much smaller than full rows if you look at the DRAM structure, which I'm not going to go into. So you can enable actually operations at 512-bit level. So you just use the mats that you need for an operation, as opposed to using the entire row. This improves your utilization, SIMD utilization, if in the DCA you have calculated for the GPUs, for example. And also, this enables you another opportunity. In the other mats that you're not using for this computation, you can do some other computation, right? It could belong to this application or some other application. So this is fascinating. That's why we call this MIM DRAM, multiple instruction, multiple data DRAM. You can execute multiple instructions on multiple different data elements on different mats. Okay, this is the fine-grained DRAM architecture that we could use. There's a lot of work in this area, actually. People develop this fine-grained DRAM for other reasons, meaning you access like a huge row, and in the end, you need only 2 bytes out of it. Why do you access the entire row, right? That's a lot of energy inefficiency. There are other benefits to fine-grained DRAM than what we do. Okay, I will not go through everything over here, but Geraldo, who was my last PhD student to graduate, which is going to change next week because Rahul will graduate. I don't know if he's here. He's working on his defense slides probably and practice. But essentially, this eases programmability. Geraldo actually developed a compiler based on LLVM to map the operations. I will not go through this in detail, but the compiler does auto-vectorization. It does some data mapping and scheduling, and then it creates a binary automatically, transparently, complete transparently to the programmer. Of course, this works if you can do auto-vectorization nicely, so it's limited to programs where auto-vectorization works, which is very limiting, in my opinion. So there's more work to be done in this area to make this better. But for those programs where it works, where you can map the data nicely across the entire chip, and you can exploit the entire chip-level parallelism, you get significant energy efficiency benefits and performance benefits compared to CPUs and GPUs. And the reason is every single cell inside DRAM, billions of cells, they're all doing computation concurrently. Whereas if you look at a CPU or GPU, there's a lot of overhead. A very small fraction of it is doing computation. Everything else is basically moving data and catering for the computation, right? Okay, so in the given time, I will quickly talk about the existing DRAM chips. Okay, we have time. You can ask questions later, maybe. But are there any burning questions so far? So far, I've shown you all simulation results. But we did a lot of studies to show that existing DRAM chips are already quite capable. This is the PyDRAM infrastructure, which Ataberk developed. It's a messy infrastructure right now, and it requires some more work to develop it even further. I think there's a lot of potential in this area. But this work showed that you can violate the timing parameters in DRAM to do a row clone and also do true random number generation. It's an end-to-end framework. And the idea is you have a RISC-V processor in the FPGA. It's executing a program, and the operating system is changed such that you can map the data, the page you're going to copy to the destination page that you're going to copy into the same subarray where the source page is. So you need to change the operating system and memory mapping for that. But when the program does a mem copy from page to page, this mem copy operation gets shipped from the RISC-V processor to the memory controller, and the memory controller violates the timing parameters, does the copy internally inside the subarray. DRAM does it basically using charge sharing principles, and returns an acknowledgement signal when the copy is done to the processor. And you can actually see this happening in real hardware, which is fascinating. We have a similar way to do random number generation also in the memory controller. It turns out if you actually violate the timing parameters and if you don't give enough time for the circuit to settle in DRAM, some cells fail randomly. Sometimes they fail, sometimes they don't fail, and it can generate a random bit string based on that failure or not failure. And this is a very nice true random number generator. We've actually verified that before this work, but this way you can actually offload rand function calls, for example, to a memory controller. And we see significant throughput improvements for initialization and copy and random number generation because the RISC-V processor is actually a very wimpy processor over here. If it was more heavy processor, it would the numbers would be much more aligned with the simulation results, which are smaller actually in our simulations. Okay, so that's one example. More recently, we've shown that you can actually incorporate all of these operations, not incorporate, you can actually see all of these operations that we envision in real DRAM chips. For example, you can copy one row up to 31 other rows with almost perfect reliability. This is fascinating. This is row clone, but row clone up to 31 other rows. You clone one row to 31 other rows. It's very good for initialization, for example. You can perform NOT operation. You can perform AND, NAND, OR, and NOR operations. Again, using the operational characteristics. The way you do it is you violate the timing parameters in a particular way that enables simultaneous multi-row activation. So in multi-row copy, you first activate the source row and you violate the timing parameters in a particular way. Lots of rows become enabled, it turns out, and the data value that's in the sense amplifiers get copied there, essentially. Again, for details, you need to read the paper or ask Ismail, who's not here. He did all of this work. And all of this is open source also. You can try it yourself. In our infrastructure, you can try it. And this is 99.98% reliable, which may be possible to use it in real systems, right? If you actually are willing to violate timing parameters. Okay, let me give you the final thing, and then we're going to conclude. Basically, you can do much more. This is actually also fascinating. Again, we're going to use simultaneous multi-row activation. You can implement any bitwise function, basically. I'm going to show you one example. So these are two cells, A and B, on this subarray. These are two other cells, X and Y, on the other end of the sense amplifier on another subarray. Now, if you had the primitive to do multiple row activation concurrently, in circuit theory, what would you get? Essentially, the sense amplifier would compare the average voltage of A and B to the average voltage of X and Y. And if this average voltage is greater than X and Y's average voltage, this part will become 1. Otherwise, this part will become 0. So what we're going to do is by setting the voltages appropriately in the reference subarray, we're going to compute a function of X and Y. That's the idea. So for this, you need to set the voltage appropriately, and there are ways of doing that in real DRAM chips. VDD is easy. You basically charge up the cell. VDD over 2 is a little bit harder, but there are works from other people as well as us that show that you can do it. So assume that I've set the voltages to this, VDD and VDD over 2 in the reference subarray. What function would I compute in the compute subarray and the reference subarray? Let's take a look. The average voltage here is 3 VDD over 4. For the average voltage of X and Y to be greater than 3 VDD over 4, both of them should be VDD. In all other cases, assuming you can put VDD, VDD over 2, and 0, that's the only case, right? Meaning X and Y should be both 1 for the compute subarray to evaluate to 1 in the bit line. And that's an AND function. If and only if X and Y are both 1, you get a 1 in the compute subarray. So you compute the AND function in the compute subarray, and by definition, because there's an inverter over here, you get the NAND function on the reference subarray, right? So you get both at the same time. And OR and NOR are left for the reader to do it themselves, or listener, which is easy to do. You just need to, okay, I'm not going to give you the answer, but it's an easy answer, right? The question is, what else can you do? Okay, this is fascinating. And we've demonstrated using real chips that multi-row copy is very reliable, and NAND, OR, and NOR are not as reliable. Why? Because you're really doing computation, which is much harder than data movement, and you're not really taking advantage of the sense amplification to move the data, right? The sense amplifiers are not involved until the computation and charge sharing is done, then you amplify the data, right? So basically, there's a lot of variation effects that affect the reliability of these, but our goal was not to show that you're going to be able to use this immediately. Our goal is to show that even if you don't do anything to the DRAM chip, to the DRAM interface, you violate the timing parameters, you still see these functions, and these chips are not at all designed for this purpose. Nobody advertised these chips that they're doing row cloning computation. Right? That was our goal, basically. And this actually opened the eyes of some of the DRAM manufacturers also, because they didn't even know their chips were capable of this, which means that they didn't believe our results in simulation. They had to have another nudge this way. Okay. So this is fascinating, and these are the papers, functionally complete DRAM and multi-row copy. And there's more to be discovered, in my opinion. But I'm going to stop here because we're already over time. This is a good question to leave you with, actually. What else can we do with using commodity memories, violating timing parameters? And also, what else can we do with memories in general? Okay, I've taken a lot of time. Any questions? No burning questions. You can always ask it in the future because we're probably going to cover some papers related to these topics. Okay, I'll see you next week then. Take care.